Okay, so let's get started here. So this is our third meeting, and today we're going to walk through every step of the PCB design of this little voltage regulator circuit. I'm going to start out by showing you some parts and do a little demo here on the doc cam, and then I'm going to attempt. Well, I'm going to open up KiCad and I'm going to attempt to walk you through, and we'll see if I'm able to do it. That is, I'm able to get the hand-eye coordination here onto that screen in a way that you can see with only one screen. And if that doesn't work, then what I'm going to do is just drop back and I'll do a recording, a Zoom recording or something, and then I'll post it, right? But I did, encourage you to bring your laptop and have KiCad up and running so that you could follow along with me if you want, just so you can, start to get the muscle memory going on using this tool. Okay, so what's the circuit we're building, right? Well, if we just start out, it's just this voltage regulator, and this is in the form factor of a typical moderate power transistor. You'll find smaller transistors, you'll find bigger ones that can handle a couple of amps of current, and they tend to be this size if they can handle a couple amps. Smaller transistors that you might have used before, 2N3904, 2N2222, 3906. If you haven't touched this stuff yet, you'll see them in SDP. They're smaller, right? This one, it's not huge, but you can see the size of that transistor. There's a ruler, and you can see scale on a tenth of an inch sort of basis. Okay, so very first thing here, if you look at the leads on that, nice. Okay. Oh, come on. It can't handle the reflection, apparently. The leads are a tenth of an inch apart, exactly. And a tenth of an inch, or 2.54 millimeters, that's the spacing on a breadboard. So if you've done breadboard work before, these things, you have to sort of force these fat leads in there, but they fit right into a breadboard. The pitch, the spacing between the leads, a tenth of an inch, 2.54, and that's the multiple that we're going to be working with in the size of these things. Okay, much of PCB design, it really involves. There's the electrical part, but that's sort of done and straightforward. It's getting all the sizes right, getting all the footprints right. And so what we'll do on KiCad when we get going is we'll first build the schematic representation there. KiCad doesn't care how pretty the schematic looks. What it wants to know is what gets connected to what, right? And that's called a net list. Then we'll go and build the board, and what KiCad cares about there is how big are the different parts and what are their footprints. And so what we're going to care about is a symbol for a part and its footprint, which is the footprint will translate to the size of the holes that get drilled by the manufacturer, the size of the copper pads around the holes that you solder to, and things like that. So a lot of this PCB design is about physical size and form factor and things like that. Okay, so our circuit's simple. One of these devices, voltage regulator, it's got 3 pins, V in, V out, and ground. You put the input pin greater than 5, greater than 7. You're going to have 5 volts at the output, and you've got a common ground. When you build a circuit, out of it, the manufacturer said you should put some capacitors in there. We're going to use, let's see if you can see this, they're little tiny capacitors. There's a 0.22 microfarad capacitor on the left, and there's a 0.1 on the right, and you can see the one on the left is sort of twice as big, right? These are tiny little capacitors. They're low voltage capacitors because we're not dealing with any high voltage, and this will just help with some transient suppression that could happen when you've got, if this is feeding something like a microcontroller, a lot of different timing signals turning things on and off, you could be pulling on the power supply, and these little capacitors help damp out some of those transients. Okay, what else do we need? Well, we need some way of getting our input voltage pair there, our input, V in and ground. So we've got some headers for that and some headers for the output. Whether we actually use these pin headers so that you could put a wire connector onto it, or we'll just leave the holes and you could solder wires onto it. We haven't decided that yet, but we're going to use the symbol and the form factor for this simple two-pin header, and that's a header with a pitch of 0.1 inches or 2.54 centimeters. So it's the spacing between those pins. Okay? All right. What else do we need? We've got a switch, right? And we talked last week about we're going to use why we're using this particular switch. It's a double pole, double throw switch, and by having two different pole positions, then that has sort of built into it a way of measuring current, the current drain from the battery. And remember, the customer here wants this power supply to provide 5 volts at the output, maximum 100 milliamps. They want an on-off switch. They wanted an LED. They wanted a way on the board to measure V-in, to measure the 5 volts output, and also to measure the current drawn from batteries. And that's because the customer wants to hook this thing up to batteries and see how long they last. So much of PCB design involves finding the part, looking at the data sheet for the part, and looking at the footprint for getting the symbol for the part for the schematic, and then the footprint, which has all the mechanical specifications. KiCad is so I had not used KiCad prior to November, and it was when the SDP team asked me could we introduce PCB design in SDP, and I was thinking, yeah, I think this is just the thing we're looking for in JDP. So that's when I cracked open KiCad and started to learn that particular tool. There are other tools that are out there for doing PCB design that are more professional and much more sophisticated, but they have a longer learning curve associated with them. So KiCad is open source, and it's got a quicker learning curve. But it's got some little quirks in it, and one of the things it has is a relatively limited component library. And you'll see what I mean by component library. It's all the different components you can choose from a menu and plop down onto a circuit board and their corresponding footprints. So what I've asked you to do is download the DigiKey KiCad library, or add that to your KiCad installation, so we'll have access to that additional set of components. And even still, you won't have everything you need. So much of the time, we're actually out looking for the CAD design for a particular component that we want to use. And that was the case with this switch. So this switch was chosen by our Colin Del Senor, who, in addition to choosing the switch, also designed a CAD model and a footprint for it. And so that's something you'll want to download into your KiCad installation, and I'm going to show you how to do that. Yeah?
I can't add the library.
You can't, I mean, so you were unable to so far.
I tried to, wanted to drag into the app, into the library to where all the apps.
So you're talking about the library for all of DigiKey, or just the switch?
Just the switch, yeah.
Okay, so I'll do it here, and then we'll see after I've done it. We'll see if if that sort of uncovers anything, and if not, we'll talk about it after class. All right. Okay, just sort of continuing with all these pieces, we also needed an LED and a resistor, right? So that's sort of the exploded view of our simple circuit that we're going to build. Now, you want to breadboard something before you go off and build it. For a circuit like this, that's not too critical because there's not a whole lot going on. Yeah?
Sorry, just about that switch. I saw the thing about installing the DigiKey library. Was there something else that installed on a switch?
Is there what?
Something else that installed on the switch?
There is, yeah. So I'm going to show you. Yeah, I'll show you what that is. All right, so I'm going to show you this on a breadboard. We're going to test it a little bit because that's good practice to do. Even though for a circuit like this, that's not too critical. After we finish this one, we're going to get into doing a digital thermometer. I guarantee you, if you don't thoroughly test that thing, hardware and software on a breadboard, before you send it off, I guarantee you it won't work when it comes back. And just sort of to illustrate some of the issues, here is a PCB that I made for this. Okay, let's see if we can get it to focus. I'll pull the ruler out of the way. So it's a little over an inch long, about half an inch wide. I wanted to make it small. And let's see if I can zoom in or anything. All right, there we go. So, yeah, do I dare introduce the ruler again? Yeah. All right, take the ruler out. So it's tiny, right? And I don't have the switch on there. And just a couple things I want to point out. So it's a relatively simple PCB. This is the one we're going to design right now. And you see it's still kind of blurry, but we're you know, the signal is flowing from left to right. And just when I was building this, some of the things I found immediately is that the capacitors didn't quite fit on there, because I bought some capacitors that had a 5 millimeter or 0.2 inch pitch. So that means that they would sit in not adjacent, but you know, they would span a gap between two. They take up sort of 3 pins, a breadth of 3 pins on a breadboard. Those are the caps I ordered. When I did the board, I actually chose a footprint with only 0.1 inch. So you can squeeze them in, right? But you have to really kind of crush the pins to get them in. So I inadvertently chose the wrong footprint for the little capacitors. Likewise, the resistor. I had to squeeze that resistor in. I chose a footprint corresponding to a 1/4 watt resistor, and I happen to have, no, for a 1/8 watt, and I happen to have a 1/4 watt resistor, which is physically bigger, so I had to squeeze that in. And then the chip itself, I had put it in backward without realizing it. I didn't leave myself sort of instructions on the silk screen of the board that told me, put the chip in this way. So I soldered it in the way it sort of made sense, because I had designed the thing several weeks ago, and it's in backward. So a simple circuit, and I've got a handful of problems associated with it when I made the board. It's not that the circuit doesn't work. It's thoroughly tested and all that. But just going to the board, there's just all kinds of ways to make errors. Okay. So to test this little board, this little circuit, here we go. So I put it on a breadboard. I don't have the switch on there, so I kind of, I'm going to simulate the switch with just a wire that I jump between a couple of different positions. And so I've got one battery pack here that's 6 volts, and another one here that's also 6 volts. So together they're going to give me 12 volts. So that's my input. And immediately we see it's not glowing. So what have I done wrong? Yeah, I got to turn it on. Yeah. Oh, thank you. All right. Yeah, that's right. If only were always that easy. Okay, so right now for a load, I have this little motor. And it's running. If I put my finger on it, it's not getting, it's warm, right? Why is it warm? Well, it's 12 volts going in, 5 volts coming out. So that means that there are 7 volts being dropped across elements inside that regulator. How much power? Depends on the current. This little motor is probably drawing about 100 milliamps. So I'll show you that I can show you that now. We want it on the board to be able to measure current. So if I move the switch to the position where in order to get it to run, I have to hook up my current meter. So now I'm going to introduce the meter to the circuit. Come on, zoom out, man. All right. All right, let's see. Turn this on. Measure current. I want DC. And so when I just close the circuit here, okay, it's running, and you can see, you can't quite see it where you are. Let me move this over. Okay, so it's about 100 milliamps. And so we said that it's close to 100 milliamps. We said that's sort of the maximum that we want to go with this thing. But I just wanted to show you what would happen if we were to just the same motor on there, but all I'm going to do is, while I'm measuring the current, I'm just going to load down the motor. And so I don't have enough hands to do everything, so I'm going to put these probes on here to measure current. But if I could get 2 other people to come up and help, I want one to just pinch the shaft of the motor, and that'll load it down, and we'll see the current going up. And I want the other one to put their finger on the 7805 until they choose not to keep their finger on the 7805. All right? All right? So, anyone? Come on down.
Oh, Dylan. What joy.
Okay, okay. So who wants to do the motor?
I'd like to be in pain, please.
Okay, so you got pain and you got the motor, all right? All right. And I have to get my probes in here. Okay? So don't load it down yet, okay? Let's just get it running. And tell us how and do you feel any heat?
Not yet.
Okay. So now give that a good loading. You can even stop it. Go ahead and stall it. That'll try to deliver maximum torque. Is that getting warm?
A little bit.
Just a little?
Now it's getting very warm.
Okay, stall that motor. Just pinch it all the way down.
Yeah, it's getting hot.
It's getting hot?
Yeah,
How hot?
pretty hot.
Pretty hot? Okay. All right. Okay. That's good. Thank you. Thank you, gentlemen. So we have no heat sink. We chose not to put a heat sink on there, right? Because we said we're going to design this thing for a maximum of 100 milliamps. But if we put a load on there that tries to pull it, it'll take it and it'll get hot, and this thing will damage itself, right? We could, if we wanted to, we could put a fuse in there that would burn out at 100 milliamps, and that could protect it, right, if we wanted to be complete, right? So just because we wanted to design for a maximum of 100 milliamps, if you choose to pull it from it, the 7805 will give it to you as much as it can, right? Okay, if we were really in the business of making a power supply and we really wanted to understand this thing, there are all kinds of things that we would have to do. We'd have to see what happens as the batteries age and their voltage drops. What does that do here? We would want to measure how stable that output is as you change the load and as you change the source voltage, things like that. But we're not going to do all that extensive kind of stuff, okay? What I want to do now is just get in and start to build the PCB, okay? And I want to show you one more board. This is what we're going to start looking at next week. So I'm calling this Megatemp. This is a digital thermometer and it'll run off of a 9-volt battery. But you can see our power supply is up in the top left. So that whole section, I've got some different capacitors in there because that's what I had on hand at the time. But that is the subsystem of this whole thing. So we're going to go through the details of this next week, and I'm going to discuss lots of different issues with you, but your big project is to redo this with an AT Tiny, and you'll find that you have to use a different voltage regulator and various other things. There's a TMP36 temperature sensor down here. You used that last year if you took 231 with me. When I built this board, I couldn't fit the leads of that sensor onto the board. The board came back, the holes were just too small for the actual size of the leads. And I just wasn't careful enough in choosing a footprint associated with that component. So this whole business of choosing the footprint for the component, getting the right drill holes and all that kind of stuff, it's a big deal. It's a common place where things can go wrong. So, okay, so let's go ahead and switch over to